So we're very happy to have today at the seminar Lev Buhovsky, who's going to talk about the Arnold conjecture, spectral invariants, and C0 symplectic geometry.
Okay, so first I want to thank very much the organizers for the invitation. So I want to give some overview of recent results on the C0 Arnold conjecture, and my talk will be based on a joint work with Vincent Lemillier and Sotkan Seyfadin. So let me start with the formulation of the Arnold conjecture, which I'm going to talk about actually. So uh, the statement is that if we have a closed symplectic manifold, then any Hamiltonian diffeomorphism must have as many fixed points as cup length plus one, where cup length is the maximal number of homology classes in M of non-top degree such that their intersection is non-zero. So this is a so-called degenerate version of the Arnold conjecture. It's not the most general one. So generally, the conjecture says that number of fixed points is at least the minimal number of fixed point of critical points of a smooth function on M. But this is some statement which is actually motivated by this one and by result from Lusternik-Schnirelmann theory, which I will talk a bit later. So, so this statement is called degenerate because it applies for all Hamiltonian diffeomorphism. So we do not assume that this our Hamiltonian diffeomorphism is non-degenerate. And if for non-degenerate case there is much better lower bound. So, but let's stick to this formulation. And first of all, this conjecture was studied a lot and motivated development of symplectic topology. And for example, for the for surfaces, it was studied by many people, and for instance, Eliashberg gave proof in the general case of a closed surface. Then for CPN, this statement was proved by Fortune, for the torus by Conley and Zander, and in the symplectic spherical case was proved by Floer, Hofer, and Rudak and Dupré. But in general, this statement is widely open. So now, actually, the subject of my talk is the continuous version of the Arnold conjecture. So the natural question I want to ask is that does the Arnold conjecture hold if we do not assume that the map phi is smooth? So of course, one needs to make sense of that and define what is non-smooth Hamiltonian. Okay, now I cannot say it's a diffeomorphism, so it's I will look at the continuous category and consider Hamiltonian homeomorphisms. And in general, these notions such as Hamiltonian homeomorphism and more generally continuous analogs of symplectic notions like symplectomorphism, Lagrangians, are a subject of study of C0 symplectic geometry. So what is a Hamiltonian homeomorphism? That I'm asking about. So this, the definition is very simple. So we say that a homeomorphism of a closed symplectic manifold is called Hamiltonian if there exists a sequence of Hamiltonian diffeomorphisms which uniformly converge to phi. And we denote by Ham bar, it's a notation for all the group of all Hamiltonian homeomorphisms. And in general, these notions were studied in dimension 2, and actually the Poincaré-Birkhoff theorem is a result in the direction of the Arnold conjecture for homeomorphisms. And also Brouwer studied the two-dimensional case a lot. And it turns out that, in fact, if we ask the same question about Hamiltonian homeomorphism, then the Arnold conjecture does hold in dimension 2. And this was a theorem of Matsumoto, and later on it was reproved by Le Calvez by his methods. So let me say more precisely what is the statement actually. So the theorem, it applies to closed surfaces, and we have the sphere and surface of genus at least one. And so what does it mean? In the, I'm sorry, this is, just a second. Oh, I'm sorry, I opened the wrong file. So can I switch to, I'm very sorry. I will do a new share. Stop share. Yes, okay. Okay, so I'm very sorry. So this, so I want to explain a bit the statement, more precise statement of Matsumoto theorem, and it talks about surfaces, closed surfaces in dimension 2. It's the sphere and the surface of genus at least one. In this case, so I should have been written cup length of sphere is 1. So this actually means that the lower bound for number of fixed points of a Hamiltonian homeomorphism of the sphere is 2. And in case of surface of genus G, the lower bound is 3. The cup length is 2. So any Hamiltonian homomorphism of surface of genus G must have at least 3 fixed points. Okay. Just one more second. I want to make sure. I again end up with a wrong file. I'm sorry. Well, I don't know what is happening here. Yes.
You can do it, Lev.
Yes, I also hope. Just a second.
But that file seemed to be interesting too. So
I'm sure, but it ends in the middle, and that's the problem.
okay.
Okay, now it's. I hope now it's correct.
How many files you have?
Oh, I think a lot. I didn't count, but let's just a second. I will check first before continue. Why does it? Okay, just a second. Maybe I'll share a screen. It's maybe a better idea. So is it okay now? Do you see?
It's very good, yes.
Okay, so now it's okay. Okay, so let's continue. I'm sorry. So this is the correct. I see remarks in chat, and you're completely right, Octave and Helmut. So now I fixed it. So so in the case of the two-sphere, the cup length is 1, and the lower bound for the number of fixed points is 2. And for the surface of genus G, torus, and so on, the cup length equals to 2, and the statement that number of fixed points of Hamiltonian homeomorphism is 3. And what are actually the Hamiltonian homeomorphisms in this case? So in case of the sphere, one can show that it's just area and orientation preserving homeomorphisms. Each such homeomorphism is Hamiltonian and vice versa. And in case of torus and high genus, it's all again area and orientation homeomorphisms, orientation preserving homomorphism, but they are also required to be isotopic to the identity and have zero mean rotation vector. So this object were studied already a lot in topological dynamics. And so this is a statement of Arnold conjecture in dimension 2. And it's also natural to ask, does the statement hold in higher dimensions? And the answer is that actually it does not hold at all as stated. And this is a joint theorem with Vinson and Sobhan, that we always can find, oh, sorry, I forgot to say it's, of course, any closed connected symplectic manifold of dimension at least 4, one can construct a Hamiltonian homeomorphism with only one fixed point. And so this, when you see this statement, you might think that there is no chance for the C0 Arnold conjecture to hold in higher dimensions, but still one maybe can hope that something in the rigidity side can be said. And we can ask, so how we can save the C0 Arnold conjecture? And the answer is that, in fact, one can do it by formulating it not just in terms of the fixed points, but also in the terms of the action spectrum of the Hamiltonian. Okay, I will speak about it later, but and actually this statement implicitly was present in the proofs of the original Arnold conjecture. So in order to discuss this more general version, I want to make a digression and speak about Morse theory, or more what is more. Oh, this Arnold conjecture is not true. Okay. At least in some cases it is true. I will show
Yeah,
you.
no. He thought that one could build some weird space where it would where the number would be smaller. But I mean, but he didn't have details. But he was thinking about it.
And no manuscript is.
No, there's nothing. No.
Okay.
Yeah. So that yeah. So at this time he had done. I mean, he had started to think. I mean, he had done the work which you mentioned there, and then he started thinking about more when you have holomorphic spheres and this kind of thing. So, so he was pretty advanced in his thinking. So using maybe some spaces where you have a lot of holomorphic spheres and some complicated structure that you can kill critical points, like kill. Yeah, so I think he would have maybe succeeded so far. I don't know, or maybe he was on the wrong track, but that was his thinking at that time.
Okay, very interesting. So maybe still there is some lower bound, but it's not the cup length +1, but something else. But in this case, I want to talk about actually the case when it is true, and I will concentrate on it. But now I want to make a digression to the Lusternik-Schnirelmann theory. So this actually this is a replacement for Morse theory in the degenerate case, and it applies to if we have a closed manifold, it applies to all smooth functions. So let's assume that we have a closed manifold, smooth closed manifold, and of any dimension and any smooth closed manifold, and we have a smooth function and or f on m, and we want to study this function by introducing a family of subsets of m. So we just look, we take some real number t and look at sublevel sets. So this is increasing family of sets when t increases, and we can consider its homology of mt. So mt is sublevel set f less than t. So it's clear that mt is empty for t very negative and mt equal to m when t is very positive. So we have the homology for t very negative is 0, and for t very positive it stabilizes and equals the homology of m. And when s less than t, we have an inclusion. ms includes to mt, and we get a natural map from homology of ms to homology of mt. Okay, but of course, this map does not need to be injective in general. And homology can change in principle. The homology of mt might increase, then might decrease again, and so on. What I'm interested in is just consider the case when t equal to infinity. So I just look at the embedding of ms into the whole manifold M, and I'm asking when, so if we take any homology class, I'm asking at which level does it start to appear? And so this is infimum, and this is called the spectral invariant of alpha. Okay, I forgot to put alpha comma f, of course. So this is the infimum of all s such that alpha appears starting from level s. And you can see in the picture we have the torus and the height function and two cycles, different cycles. And for example, if you consider the green one, then okay, so let me say first about this definition, maybe that this is the definition of spectral invariant, but actually one can reformulate it in maybe more classical way, that it's with minimax. So we can say that it's the same as considering. So if we have a homology class, we represent it by a submanifold in M, and then we try to and we take the maximum of the function over this submanifold and try to minimize the maximum. So for example, in this green circle, we can push it below a bit, but you see that we cannot push it too much. We cannot pass the second line from above. So these lines are exactly the critical values. And the spectral invariant always belongs to the set of critical values of the function. In this example, you see that spectral invariant of the green cycle is the second from above, and spectral invariant of the red cycle is the second from below critical value of the function. So, and what is relevant for my talk is the following basic lemma from the Lusternik-Schnirelmann theory. And it says the following, that assume, so let M be a smooth closed manifold as before, and we have two homology classes such that degree of the second one is less than the dimension of M, and their intersection is non-zero. And assume that we have a smooth function such that the spectral invariant correspond to alpha intersected with beta, and alpha coincide. So this situation is kind of degenerate situation. Always we have that the left-hand side spectral invariant of alpha intersection with beta is not greater than spectral invariant corresponding to alpha. This can be immediately seen from this minimax description of a spectral invariant, that if we take a manifold and intersect with another one, then maximum can only decrease. But usually the spectral invariant of the intersection alpha intersection with beta is strictly less than spectral invariant of alpha. But if we assume that we are in such a degenerate situation that they're equal, then it follows that this critical level is large. So it's what is called homologically non-trivial. In particular, it's infinite. And I say that a subset of M is homologically non-trivial if it's for some J at homology of degree greater than 0, the natural map from homology of A to homology of M is non-trivial, has non-trivial image. And now, if we have this lemma, then we immediately get the following corollary, which is one of basic results of the Lusternik-Schnirelmann theory. I think that if we have a smooth function on a closed manifold, then it must have many critical levels. So actually many critical points, but this statement is more general, that we conclude that if we take all the classes in homology and look at all spectral invariants of F corresponding to all the classes, the number is at least the cup length plus 1. And if this is, okay, it's at least couplet plus 1, and if it's less, if this does not hold, then the set of critical point is infinite, or more generally homologically non-trivial. And you can see it immediately just by starting with the fundamental class and taking this collection of homology classes who assume that you have k homology classes whose intersection is non-zero, and you take intersection consequently with each one of them, and each time either you decrease the value of spectral invariant decrease. If it decreases every time, then we have a lot of spectral invariant, and otherwise some of the levels is large, is homologically non-trivial. Okay, so now I want to pass back to the symplectic setting, and I consider a closed symplectic manifold, which is symplectically aspherical. So the omega and the first chain class vanish on the spheres in M. And now if H is a smooth Hamiltonian function, it generates a Hamiltonian flow. And to this, we can associate what is called Floer homology. So this is Floer theory. It's a theory that in some sense analogous to Morse or Lusternik-Schnirelmann theory in this setting, namely in the case of action functional on the space of contractible loops in M. So we consider our manifold actually on which we study now is the infinite dimensional space of contractible loops, and we consider the action functional A, which is integral of H minus over the loop minus the area of the disk with boundary at the loop. And it turns out a computation shows that critical points of this action functional are exactly one periodic orbits of the flow. So if we try to do Morse theory for this action functional, we can get information about one periodic orbit of the flow or fixed points of time one map. So, and let's now try to do the same as we did before in the Morse theory. So now this setting is a bit more, so it's much more complicated, and we cannot just do the same considering sublevel sets of action functional. But instead what works is another way to build homology theory is to look at gradient flow of the function with respect to some Riemannian metric. So this is another way to describe homology theory, and this is the way that Floer did. And but here, of course, it's still not the same as in the Morse theory, and you need to adjust the theory in this setting. So here we end up with the Floer complex. So we consider the set of all periodic trajectories, all fixed points of the time one map or set of all periodic trajectories, and the complex that they generate. And we have a natural differential counting Floer trajectories, and we get a Floer homology. And this complex is filtered, so we can now look at for any number t, we consider the complex generated only by periodic trajectories of action less than t, and this gives us for any t a Floer homology group. And again, as before, if t is very negative, the Floer HF less than t is 0 because we do not have periodic orbits at all. And if t is very positive, it's just coincide with usual Floer homology. And Floer have shown that, in fact, the Floer homology always of any Hamiltonian is always isomorphic to the singular homology. And therefore, we can define in this setting spectral invariants corresponding to cycles from the homology. If we have alpha, we here also in a similar way define the spectral invariant as infimum of all t such that this cycle starts appearing from the level t. Okay, so this is the definition which mimics definition from Lusternik-Schnirelmann theory. And the important property of these spectral invariants was proved by Schwarz and Seidel. It's true in the symplectically aspherical case that, in fact, these spectral invariants depend only on time one map. So what do I mean by that? That they depend, if we have a Hamiltonian diffeomorphism phi and consider any normalized Hamiltonian function, so we assume that its integral is 0 at any time, then the spectral invariant does not depend on such function. Or in other words, if we have arbitrary two Hamiltonian function which give the same time one map, then the spectral invariants for one function and are just shifted spectral invariants of the other function. So the constant that we shift is just normalized average of the difference. It's just average of the difference of the two Hamiltonians. Oh, I'm sorry. I need also integrate by the time here, of course. Okay. So now I want to conclude something from this statement, from this result of Seidel and Schwarz. So first is that, of course, spectral invariants are well defined up to shift of any Hamiltonian diffeomorphisms, and in particular, the number of spectral invariants of Hamiltonian diffeomorphism is well defined. And now it was an observation of it was a paper of Wyatt Howard, who actually saw that the statement from Lusternik-Schnirelmann theory that I described hold also in the symplectic setting. And I think these results also were obtained by Floer and Hofer before. Am I right? They are implicitly, they're not stated in the paper, but they follow from the paper.
Well, in my paper, so I obtain a flow on a compact metric space and have an index, and if two characterizations are the same, then this set of fixed points has a positive index or an index bigger than 1, and then it must be an infinite set.
Mm-hmm.
Yeah.
I see.
And presumably Floer is similar.
And Helmut, that space in your case mapped by a degree 1 map to the initial manifold. Is this
right? Yes. So it is a space of perturbed pseudo-holomorphic strips, and there's an evaluation, say at time 0, going into the manifold, and this injects in cohomology into that. And of course, since you have strip, you have this flow, and you can integrate over a line, and then that's a functional, and so it's some kind of a gradient type flow on this space.
And the reason why it's injects in cohomology is because it's a degree 1 map.
Mm-hmm. Right.
So you check it in on, yeah.
Mm-hmm. Okay, thank you. So this, okay, so let me first say, so the results from the Lusternik-Schnirelmann theory I discussed is the lemma and corollaries of the corresponding lemma in the case, in our case, states actually the similar thing, that if we have a closed symplectically aspherical manifold and Hamiltonian function and two homology classes with the same condition, and the spectral invariant of alpha intersecting beta and alpha coincide, then the set of fixed points of the time one map of the same action is homologically non-trivial in M. And from here we get the corollary, which I state as a theorem, that if we have a closed in the closed symplectically aspherical case for any Hamiltonian diffeomorphism, either the numbers of spectral invariants is at least cup length plus 1, or the set of fixed points is homologically non-trivial, and in particular infinite. And so the first result in C0 symplectic. Okay, so now I want to address the C0 Arnold conjecture in higher dimensions, and our joint result with Vinson and Sobhan actually says that Hoover's theorem holds also for Hamiltonian homeomorphisms, again in closed symplectically aspherical case, but in any dimension. And this is just an observation. In some sense, one part of it is an observation that the Hoover's proof passes through this homeomorphism. It extends quite easily to the setting of Hamiltonian homeomorphisms. And later on, Kawamoto has shown the same for CPN and negative monotone symplectic manifolds. But actually, the statement is not completely clear yet, because, okay, it's a statement about spectral invariants of of Hamiltonian homeomorphism, but I didn't say what are the spectral invariants. And if we have in general Hamiltonian homeomorphism, then there is no sense to speak about the Hamiltonian function. It is just a uniform limit of a sequence of Hamiltonian diffeomorphisms. So each one of these diffeomorphisms, it has a Hamiltonian function, but we do not have any type of convergence for Hamiltonian functions, and we cannot do Floer theory directly for Hamilton in this case. And so this is now the question that I want to ask. So what are the spectral invariants of Hamiltonian homeomorphism? And it follows that although you lose connection to Hamiltonian function and now the setting is continuous, one can still define them because of certain continuities, zero continuity of spectral invariants. So, and to better describe this zero continuity, I want to first recall definition of what is called spectral norm. It's for Hamiltonian diffeomorphism on symplectic manifold, and the spectral norm is just, by definition, the difference between the top and the lowest spectral invariant. Spectral invariant corresponding to the fundamental class minus spectral invariant corresponding to the point, it is always non-negative, and this is definition originally goes to was definition of Claude Viterbo, and later it was extended to symplectic spherical case by Schwarz, and we consider this case, and later to the general case by Ohm. And one can show that this gamma is in fact actually a norm on the group of Hamiltonian homeomorphisms, and the theorem joined with Homilier and Sefardini states that in the symplectic spherical case, this gamma norm, this spectral norm is C0 continuous. So if we have a sequence of Hamiltonian diffeomorphism converging uniformly to the identity, then the spectral norm converges to 0. And as a corollary from this, we get what I said before, the C0 continuity of spectral invariants up to shift, and the fact that they are well defined again up to shift on Ham bar. And to see this, you just can define. So for each classes alpha and beta, you can define the difference of spectral invariant for alpha and for beta. And this we can call gamma alpha beta phi. And from basic properties of spectral invariant for the difference of this new gamma for two maps phi and psi, we can bound it by twice this spectral norm of phi inverse psi. And because gamma is C0 continuous, we immediately see that for any two alpha and beta, the difference of two spectral invariants is continuous, C0 continuous, and also that by looking at Cauchy sequence, we conclude that we conclude that it extends to Ham bar by approximating it by a sequence, taking a sequence of Hamiltonian diffeomorphism conversion, and we can naturally define gamma alpha beta phi for element of Ham bar, which means that spectral invariants are well defined up to shift on Ham bar. So I see. Oh, I'm sorry. Yes, I will fix this later. A typo in Schwarz. Okay. So, so actually, this result is in new setting, but this particular statement was studied before, and it was proved much earlier by Claude Viterbo that yes, I said t equal to 1. I'm not sure.
It's a joke in Schwarz.
Okay. So this result was proved by Claude Viterbo in case of R2n. Then it was extended by Sobhan Seyfadini to closed surfaces and some high-dimensional cases, but these cases consist of open manifolds. And recently we have a result of Shilukin who showed it for CPN. And okay. And actually, Yegor showed much stronger result, the Viterbo conjecture in the case of CPN, but it's a maybe different story. And also Kawamoto extended it to negatively monotone symplectic manifolds. So now I just want to remark that about this result. If we go back to the conclusion that spectral invariants are well defined for Hamiltonian homeomorphism, in fact, in general, spectral invariants only give some partial information on the filtered Floer complex, and better information one can get by looking at the barcode. So I just want to say a few words about it. Let's come back to the again to the Lusternik-Schnirelmann theory that we discussed before, and we discussed that. So given a function on a closed smooth manifold, we look at sublevel sets, and we have inclusions of sublevel sets, and we have this family of maps between homologies, and this is a certain object that we have a family of homology groups and vector spaces and maps between them, which are natural. And this is in general called the persistent model. And a way to describe it, so this family of homologies and maps, it detects the situation when the homology at some levels it might increase, at some levels it might decrease, and so on. And way to encode this information, it can be by what is called barcode. So each time a homology class, at the moment when homology class appears, a bar starts to grow, and when it disappears, it ends, and we get an interval of the real line. So this is can be a picture of a barcode. And some homology classes, they persist to infinity, and they correspond. So these are infinite bars that corresponds to homology classes of the manifold. And the same can be done in the case of Floer theory. And actually, the result that I discussed, the C0 continuity of spectral norm, implies not only that we can define spectral invariants for Hamiltonian homeomorphism up to shift, but actually the whole barcode up to shift, and it's based on another result of Kislev-Shilukhin, who have shown that the barcode depends continuously on the Hamiltonian diffeomorphism and on the Hamiltonian function, and continuously with respect to the gamma distance. And if we know that gamma distance is zero continuous, then we get that barcode depends continuously depends zero continuously on the Hamiltonian diffeomorphism, and this allows to define actually the whole barcode for any Hamiltonian homeomorphism. And in dimension 2, this was previously shown by Leroux, Fadini, and Viterbo. And now I want to conclude the talk by returning to the C0 Arnold conjecture. So if we recall, so we have the original statement of C0 Arnold conjecture does not hold in high dimensions. One can always find a Hamiltonian homeomorphism with only one fixed point, but for such Hamiltonian homeomorphism, the theorem says that it still must have a lot of spectral invariants. So in high dimensions, the fixed points somehow lose a certain role. So the high dimensions can allow to collapse several fixed points to one point. And this is actually some idea how construction of such counterexample goes. But let's now return to the two-dimensional case. So in the high-dimensional case, the high dimensions allowed to collapse the fixed point, but maybe in the two-dimensional case, the fact that the dimension is low, this fact does not allow to collapse the point. And there is a hope that many spectral invariants, existence of many spectral invariants that guaranteed by the statement, this more general statement of Arnold conjecture, of C0 Arnold conjecture, together with the fact that dimension is low, will lead actually to many fixed points and will give an alternative proof of the results of Matsumoto. And this is a part of a work in progress with Vincent and Sobhan, and I just want to conclude with formulating a lemma. It is not written yet, but this is actually the main lemma in this for this two-dimensional setting, and it states that if we have a closed surface, closed symplectic surface, and assume that we have a Hamiltonian homeomorphism with finitely many fixed points, P1 till Pn, and the statement is that we can always approximate this phi by a Hamiltonian diffeomorphism in the uniformly up to any epsilon in such a way that we have the following. So, of course, if we have our fixed points of phi is P1 till Pn, then any psi which approximates phi, its fixed points are located near the fixed points of phi. So each fixed point, if we have a psi which is very close to phi, then each of its fixed points is very close to one of the PIs. And the statement is that we can always find such psi such that near each PI, the fixed points of psi have almost the same actions. The difference between actions of any two fixed points is very small. And this is, given this lemma, one can, it's already not difficult to see how one can recover the Matsumoto result, at least in the case of the genus 1 and higher genus closed surfaces, but also for the sphere, one can do a similar thing. And I just want to remark that, okay, of course, for the sphere, the action functional is not single valued, but one can still make sense of saying that if we have two fixed points of psi near some pi, that the action difference is small. We just know that pi is a fixed point, so we can compute, if we have two fixed points of psi near pi, we can connect them by a curve and look at its image, and both the curve and the image lie in a small neighborhood of pi. So the area between this curve is well defined. So one can look also at such definition of the action difference. Okay, so So actually, this is all I wanted to say. So I want to thank you very much for attention.
Thank you very much. A lot. So any questions for Lev?
Yes, I have a question.
Mm-hmm.
Is there any dynamical meaning for this spectral invariants? So apparently, I mean, when they're different, so apparently they don't correspond to fixed points, but would they correspond to something else, like invariant measure or something?
I don't know. So you can maybe ask if we approximate better and better our phi, then you get more and more fixed points, and you can collect more information from them. I don't know. So in general, I think one can also consider the case when you don't have just finite number of fixed points, but a set of fixed points. And some maybe there is a hope that similar statement holds for connected components of the set of fixed points, but I cannot say for sure.
What do you mean by the same statement holds for connected components of fixed points?
So if you have,
you could have only one.
Sorry?
In the end, you could have only one fixed point.
No, I'm looking, maybe you asked about higher dimensional case or lower?
Yes, higher dimensional, sorry, higher dimensional. So when you have several spectral invariants, but which are distinct, but you only have one fixed point. Can you say something about the meaning of the different spectral invariants? Is there any dynamical meaning for that?
Sorry.
Yes, please.
No, just my feeling is that it's more some kind of a multiplicity of the fixed point. But even this is not really clear because it's not a local thing, the spectral invariant. So you don't really know which fixed point carries it. But somehow you could have one fixed point with a multiplicity given by the cup length.
But if you have two, for example, can you say which classes are carried by one and which ones are carried by the other?
It's a very good question, but I don't know.
Yeah, I think we would like to understand that. But
in dimension 2, there is a hope to construct the local Floer homology, and in dimension 2, it's hope to better understand this situation. There is this. Can you say something about the indices of the perturbed fixed points?
Is it clear what's different in dimension 2? Except that you cannot construct the counterexample. But is it clear why suddenly somehow the spectral invariant different spectral invariant have to give you different points in dimension 2? Is there?
That there is no way to collapse.
No, I understand.
I don't have another explanation.
I understand that you cannot construct the counterexample because of your construction.
Somehow, if you have two fixed points which are close and you connect them by curve, then image of this curve must be.
No, I understand that I heard the construction. It's clear that it's not going to work in dimension 2, but do you have any?
I think the action in dimension 2, the action of a closed curve is well defined, even if it's only continuous, because you can measure the area in between, enclosed.
Yes, maybe this is a good answer.
Higher dimension, if it's only C0, I don't think you can define something.
Oh, okay. Okay.
That's not what you just said.
Okay, thanks. poser des questions?
There is a question about indices of perturbed fixed point, but we didn't think about this. I think we actually abandoned this project for a while, so I hope to return to it soon.
I have also a little question. So did you guys look directly at this spaces X, the spaces that Helmut constructed basically of pseudo, because another way to think about it is you have this sequence of spaces that come with degree 1 maps into evaluation maps into the manifold. And okay, I think Helmut is still here. I think you're here. You're muted, but you're here. So
yeah, I was partially here, but I know I'm here.
So these spaces come with a filtration, I think. In any case, with a gradient-like flow and with some filtration. And you could think, okay, when you have the sequence that tends to the Hamiltonian homeomorphism, what's happening with these spaces? And is there any way in which you can make sense of a limit for these spaces? Because they come with some common properties topologically, in the sense that they come with this degree 1 map that basically it's a basis of proving the cup length inequality in the smooth case. And so you could say, okay, if I make sense of the limit of these spaces in some way, then okay, maybe it's a more global way to. It's a question. I don't.
So we should look at the paper of Helmut.
So my feeling is that as soon as you have spaces that come with a filtration and with gradient-like flows, there is a notion of a meaningful notion of limit inside this category. And all these results about stability in C0 topology basically come from the fact that somehow filtrations are dominant when you look at complexes or chain complexes and things like this, and it's not the smooth structures that matters, but the filtration sort of that. And so maybe one can do something at the level of these spaces with, I don't know, it's just a question. I just had this, I was wondering.
Okay, thank you for suggestion. Actually, the question about holomorphic curves and this C0 setting, I think nobody.
Yeah, so in the plane, of course, you can sort of take L infinity J's. Yeah? So maybe, I mean, you need some bounds on from above and below how it distorts, but if it's L infinity, you have Riemann mapping theorem. So yeah, well, I think one should study what one can do in higher dimensions, but nobody did. Maybe nothing, I don't know.
But Helmut, the way I was thinking about it was a bit different. So I would take
No, I understand. No, I was answering. No, I understood what you said. So in what you said, yeah, so you have, so in that paper, essentially, you look at you start with C infinity functions from cylinders into the symplectic manifold, and you have the R shift on this, which is a flow on C infinity functions. And then you construct a topological space, which is an invariant subspace of this, which carries the homology of the underlying symplectic manifold. And you have and in fact, you have a globally defined function on this stuff evaluating, say, at the loop at 0, at time 0. And then if you restrict it to the subspaces, then you get a gradient-like flow. So now this subspaces which you have, you want to take a limit of this, even if it doesn't really exist, yeah. But you want to have a virtual limit of this stuff, yeah.
Yes, but you see, yes, but in fact you can do a virtual limit because there is a telescope in this setup. So you don't need to really take the limit of the points in your spaces, but you can kind of have comparison maps between one space.
Right. If you shift from here to here and you have the next one, they are interlaced in some sense. Yeah.
And sort of a priori, because this sequence of things does stand somewhere in C0, because it's a whole definition of the things, and maybe this telescope, infinite telescope, makes some sense. That's a question. And
can I ask also a question? Where can I read about this? Because actually I don't understand.
You pick
anything.
Octave's brain.
No, but this is Helmut's paper. I mean, I'm talking about things that I think this paper is, I don't know, 92 or I don't know, Helmut.
No, there must be a. So I did the Lusternik-Schnirelmann a little bit earlier than Floer, because Floer needed first to construct his Floer homology, and then he got it out from his Floer homology, which was much harder. So yeah, it must be 8. I don't know. Wrote in 87 around, so 88 maybe it's published, I think.
Okay.
Or I don't know. It was a longer paper, so maybe refereeing took forever. I don't know. But I was at Rutgers when I wrote this and when it was accepted. So it was before 89.
Yeah, I see it. Lusternik-Schnirelmann theory for Lagrangian intersection.
Right, but so what I'm talking about is sort of a little thinking a little bit along this line, but you know, it's just a question. I mean, I know we can talk about it if you want at some moment, Lev, what exactly my point is. But and Marco sent the exact reference. I think this is a precise reference. So it didn't take refereeing so long, Helmut. Those were much better times.
Oh, okay.
All right. All right, so let's see other questions, maybe.
Yes, I'm sorry, I have another question. If no, what happens with Hameo? So if you look at objects which have a Hamiltonian.
Yes. So what is the question?
Well, what happens then? Can you repeat the same talk with Hameo instead of?
Yes, because they are in particular.
Because
in Hameos it's much easier because the spectral invariants are well defined just by continuity with respect to the Hofer.
I understand, but do you now have correspondence in the sense that different spectral invariants will give you different fixed points?
No, actually, this counterexample was a counterexample for the same Hameos you are talking about of O and
So the counterexample is in Hameo, actually.
Yes.
Okay. Okay, thanks.
Actually, maybe I'll add a remark, Claude, since you were, you were looking at this. The counterexample, you could actually, I mean, if you're thinking of some sort of action in higher dimensions, the counterexample, you could basically produce it for any sort of reasonable definition of Hamiltonian homeomorphism. So somehow.
Okay, thanks.
That's kind of bad news for this. I mean, who knows? Maybe there is some sort of a local Floer theory
or good news. Who knows?
Or it could be good news.
I mean, yeah, facts are usually good news as far as I'm concerned.
Depends.
Well, unlike in this country here, but anyway.
Yes. Well, you have alternative facts.
But anyway, so I think whoever is in the audience, I think it's time now also to think about a counterexample to the Lusternik-Schnirelmann version of the Arnold conjecture. So I think most people maybe try to prove it, but I think Floer had a pretty good idea usually what was going on. So he thought that I mean, of course, if the Hamiltonian is small and autonomous, then we have Lusternik-Schnirelmann theory. Yeah? So I think you need a lot of pseudo-holomorphic curves maybe, and the Hamiltonian time dependent has to be large enough to sort of in a meaningful way interact with this stuff and destroys so that very few periodic orbits pick up the homology in the problem. So because I think that's presumably the technologies and everything is around. I mean, at least to make some progress on this question. I don't know what the answer will be, but rather than looking to prove this, maybe one should just try to disprove it. Sometimes just this remark extremely powerful. Yeah.
Yes.
Okay, on this word, I have to leave. I have another Zoom meeting, actually 2 other Zoom meetings lined up. So Claude, you can relax. You are the next after the one which I have now. but
I'm always relaxed, Helmut, don't worry.
Okay. Yeah, I know. That was one of my cheap jokes. But
so let's see. Helmut, bye-bye. So let's see if there are other questions for Lev. I'm just looking around. So if not, thanks a lot, Lev, again. Thank you very much.